Hey guys, welcome back to another week of Honors Chemistry e-learning. Today we're going to sum up and take notes over the three sections that you read from the CK12 website on activation energy, potential energy diagrams, and activated complex. Going to kind of shrink all that into one lesson. It's really not that much, but we're going to call this the potential energy of chemical reactions. So, of course, take the notes that are on the page. Um, and then pause and do that, and we'll talk about it. Okay, so for the first thing is you need to understand that anytime two reacting particles, or three, or however many there are, collide, they have to collide with enough energy to break the existing bonds. So when you have two particles coming together, and those particles already contain fairly stable low energy bonds, they're not just going to fall apart unless they collide with enough energy. We talked about that in our collision theory discussion. The reason they have to have enough kinetic energy is because we have to break those existing bonds. That is an endothermic process. And that's the first thing that has to happen. So breaking the old bonds is endothermic. The energy required to do that is referred to as the activation energy. So if you can imagine striking a match um, on that little gritty sandpaper surface on the box or the matchbook, that friction is supplying the activation energy to get the reaction started. If you didn't need that activation energy, then the phosphorus in the match head would react with the oxygen in the air, and that match, that whole box of matches would just, you know, uh, ignite right there in your kitchen cabinet or wherever you have it stored. But it takes a little bit of activation energy to get the reaction going. So the way that's represented in a potential energy diagram is it's the uphill part. That is the activation energy. And if we had numbers along the y-axis here, you could figure out what the activation energy is for each of these reactions that you see in these diagrams. It's just basically the distance from where the reactants were to the top of the hill. Okay, so and again, the lessons did a good job, I think, of showing basically it's like a ball rolling over a hill. If the uphill side is bigger, that means it takes a lot of activation energy, and if the downhill side is smaller, well, that means your products are going to end up with more energy than your reactants had, which means your delta H is positive, so that would be an endothermic reaction. Over here, you have the exact opposite. You have the reactants, the uphill is smaller than the downhill, so that would be an exothermic reaction. If you were to sort of sketch the activation energy for each of these, the activation energy would simply be from wherever your reactant energy is up to the peak of the hill. So that would be your E sub A, activation energy. And of course, it would be a lot smaller for this second reaction because it would just be from here to here. So for endothermic reactions, activation energy tends to be very high. It's possible for activation energy to be very high for exothermic reactions too, or very low. Um, but the downhill side of the slope is the exothermic part. So when you strike that match, the uphill, just the friction from the little sandpaper on the matchbook, is pretty small. The downhill is huge. You're seeing that flame. So there's lots of energy being given off. So probably I would say neither of these represents lighting a match. If you were to draw a potential energy diagram for lighting a match, it's going to be shaped more like the second one, but with a much smaller activation energy hill and a much larger, downhill, right? So here you're lighting a match. It doesn't take a lot of energy to get it to get the reaction started, but then it gives off a lot of energy as it goes. So a very exothermic reaction with a small activation energy. That would be lighting a match would be an example of that. So here's a couple more looks here at activation energy. Um, so what do you think about these reactions? They actually have something in common in terms of endothermic, exothermic. Yeah, you should say that they're both exothermic, the reactants are higher in potential energy than the products. That's true in the left and it's true in the right. But of course, the delta H would be a much larger or much more negative number, I should say, for the one on the left, for reaction A, because there's a bigger difference in reactants and products. It'd be very small for reaction B, because the reactants are only slightly higher in potential energy or enthalpy than the products are. The activation energy, the energy required to get the reaction going, is much higher for reaction B. You can see that uphill is much, much larger. Okay, another term that the lessons, the online lessons spend a lot of time on, in fact an entire section on, is activated complex. I'm not going to spend a ton of time on this. It is conceptually somewhat important, but it's a very short-lived part of the reaction. Essentially, it represents the top of the hill. So if you think about your reactants, your products, at the top of the hill you have your activated complex. So for example, let's say this reaction, so let's actually say that we're going to make, we are going to make H2 and I2 into 2HI. So that's a reaction. So H2, so that's the little green guys there, and I2, we'll make those, I don't know, blue. So here's a couple of, I2 would be quite a bit larger. We're not doing it to scale, but you get the idea. There's I2. And in the end, we're going to make two HI molecules. So each molecule in my product is going to have an H bonded to an I. Right? So those are my products. So you can see what my reactants look like. You can see what my products look like. But what does the activated complex look like? Well, the activated complex would actually be these two molecules combined. The bonds between them are still breaking, and the new ones that are going to form these products have already started to form. So what is that going to look like? Well, it's going to be basically like, the way we usually draw it is like with sort of like dotted lines in between the atoms. I drew it kind of small, but this is the activated complex. All four atoms are sort of loosely bonded together, and it's very unstable, and it doesn't last more than a few nanoseconds in most cases. Although, if you watch the video with the little beaker on the hot plate and the stir plate, you can get it to last a little bit longer depending on the specific reaction, but most of the time it's very quick and it's gone because it's so unstable. So that is your activated complex. It's high energy. It's always higher energy than your reactants and products, because by definition it's the top of the hill, right? So it can't be lower in energy than the reactants or the products. And then as soon as we start going downhill, the link between the H's and the I's is broken, and we're going to form our products. Okay, let's answer a few questions here. So here's a potential energy diagram. It's labeled with A through E. Which letter or letters represents the activated complex? Okay, so you should have said C, right? The activated complex would be at the top of the hill, the highest energy, and the lowest stability at that point. All right, let's look at number 2. Which letter or letters represents a point at which old bonds are breaking? I'll give you a hint here. It's actually 2 points. So what 2 points would you say old bonds are breaking? Okay, so it's not A. A is just the reactants. B is definitely an answer, because we said on the uphill it's endothermic because old bonds are breaking, and that's an endothermic process. The tricky one that you may not have gotten is actually C, because C is the activated complex, and if you remember just a minute ago I told you at the activated complex old bonds are still breaking, but new ones have begun to form. So it's kind of both are happening, therefore it fits for, the description old bonds are breaking. And then which leads us into number 3, which letter or letters, and again there's going to be 2 this time, represents a point at which new bonds are forming. So you should have said this time C as well as D. So the peak of the hill, we're forming new bonds as well as breaking old ones. And then on the downhill, point D, we are just forming new ones during the exothermic part of the process. All right, number 4, which letter or letters represents a point where the reaction system is at its most stable? So think about the relationship between stability and energy. When things are very unstable, they have a lot of energy. So if we're looking for the point where the reaction is most stable, has a lot of stability, what does that mean about its energy, and what point represents that? Okay, you should have said that it's most stable at point A, because that is when the potential energy is the lowest, meaning that it's going to be most stable. All right, and is this, the forward reaction, by the way, we're just going from left to right. You can see it's labeled here. So is the forward reaction going from left to right, endothermic or exothermic? Okay, if we just kind of draw a little dotted line representing where our reactant energy was, it is definitely going up. So we have a positive delta H, which means this is an endothermic reaction, the forward reaction. And then by definition, we haven't really talked about reversible reactions much, but by definition, if we go in the other direction, sorry, that way, it would be exothermic. Okay, so this says the activation energy for the reaction, H2 plus I2, which is actually the one that I was describing earlier, is 40.8 kcal. And don't worry about kcal. Remember, kilocalories, basically, it's just another unit of energy. So if we were using joules, it would just be a much larger number. But it's just a unit of energy. Could be calories, kilocalories, joules, doesn't really matter. Notice it also gives you this little bit of information there. So think about this for a second. If heat, and again, kilocalories is just a form of heat, just like joules or kilojoules, if heat is on the right side of the equation, the product side, is this reaction endothermic or is it exothermic? Okay, so it should be exothermic, right? So sketch a potential energy diagram where we have this amount of heat given off, and this is our activation energy. So I'm going to ask you to sketch it and try to keep your hill, first of all, draw it as exothermic, because we've already decided that this is exothermic. And I want you to try to make your hill so that the activation energy and the delta H are correct relative to each other. In other words, if I'm given this activation energy of almost 41 kilocalories and a delta H here of just 3 kilocalories, how does that affect the shape of your potential energy diagram? So go ahead and sketch it on your own in the space there, and then I'm going to give you some pictures that I drew that you can choose from and see which one best matches yours. And by the way, this reaction is the same one that I was using as an example up above, but don't let that sway your potential energy diagram. Just because I used that reaction up here does not mean that your potential energy diagram should exactly resemble this one. Okay, so just wanted to clarify that. You would need to draw a potential energy diagram that makes sense based on the information that you see right there. Okay, here's what I drew, and let's talk about why. So this is an exothermic reaction. You can see my reactants here are slightly higher than my products, and I only did it slightly higher because there's only a difference of 3 kcal. Relative to my activation energy, the size of my hill, which is very large because my activation energy was, over 12 times larger than my delta H, 41 compared to 3. So in other words, my activation energy, which would be essentially from this dotted line all the way up to that peak, is very large, 41. And the drop from the dotted line down to my products is very small, 3. So hopefully that makes sense to you, even if you didn't draw one that looks exactly like this one. Okay, one more question. It says the activation energy for the reverse reaction, what would that be? So taking a look at what we just drew, oops, just move myself here. So taking a look at what we just drew, if that's a potential energy diagram, which one makes the most sense for the activation energy for the reverse reaction? Okay, so hopefully you said 43.8 kcal, because the energy for the reverse reaction would be from, so the reverse reaction, we would be starting with products and going in reverse, so it would be the original activation energy plus the other 3 kilocalories, which were the difference between reactants and products. So now we're going in reverse, so now we have to get over an even bigger hill going back in this direction. All right, so that's our discussion of potential energy and reactions. Make sure that you do the next assigned section so that we're ready for the next video on Thursday. You guys have a good day.